Number one, in 2011, the population of deer in a forest was 650. In 2012, the population increases by 15%. Write an expression using only multiplication that represents the deer population. So remember, if we're increasing by 15%, we have 100% plus we have another 15%. So that means we have a total of 115% of the previous year. And this is happening each year. So then we want to write this as a decimal. So if I divide this by 100, we get that's 1.15 of the previous year. So for this one, we have 650, which is the initial deer population. And then we have 115% more. So then in number two, now it's asking us in 2013, the population again increases by 15%. So now we have, this original, the one from the previous year. So we have the 2012 population, and now we're multiplying this by another 115%. So you could do it like this. That's also the same as thinking about it as 650 times 1.15 two times, so to the second power. So either of those two are fine. Now, this second way of writing it is more helpful for part C because it says if the deer population continues to increase by 15% each year, write an expression to represent the population T years after 2012. So this would be 650 times the 1.15, which is a 15% increase each year, so to the T power. Number two, Mai and Elena are shopping for back to school clothes. They found a skirt that originally cost $30 on a 15% off sale rack. Today, the store is offering an additional 15% off. To find the new price of the skirt in dollars, Mai says that they need to calculate 30, the original cost, times 85.85, which is 85%, right? So if we think about this as 15% off, so if we take 100% minus 15%, that means we're paying for 85% of the original price. And that as a decimal equals 0.85. So she's saying we have to take the original cost of the shirt, multiply it by 0.85, then multiply by 0.85 again. Elena is saying they can just multiply 30 times 0.7. So for her, she's getting this 0.7, thinking of that as 100% minus 15% minus 15%. And saying, all right, we're actually just paying for 70% of the shirt, doing it like that. So calculate the cost of the skirt using both of their methods. So Mai's method, if we type this into our calculator, we would get $21.68 as the cost. If we were to type in using Elena's method, so we type in 30 times 0.7, we would get that the cost of the shirt would be $21. So then it wants us to explain why the expressions used by Mai and Elena give different prices and which one is correct. So if we look at Mai's interpretation, right? So Mai is taking 85% of the original cost, then taking 85% of the discounted price, right? So she's doing the shirt times 0.85, then taking that discounted price and multiplying by 0.85 again. So if you want to think about it as the 85% of the original. So she's taking 85% of the original cost, then doing 85% of the discounted price. Where Elena is taking 85% of the original. And maybe I shouldn't write this with 85%. Let's say my is taking 15% off the original price, then taking another 15% off the discounted price. Where Elena is taking 15% off the original price, then is taking another 15% off the original price. Since she just added the 15 and 15, she's going back to 15% of 30 and then another 15% of 30. Where my is doing 15% off the 30, then she's taking 15% off that new price. And that is the correct way. So Mize is the correct way. Mize is giving an additional discount to the discounted price, right? So correct. Number 3, $1,000 loan charges 5% interest at the end of a year, while a second loan charges 8% interest at the end of the year. So part A wants us to complete the table with the balances for each loan. And so if we go up here, so we want to do, let me get a marker here. All right, so each of them start with 1,000, right? So this one's going to be 1,000, and then we're going to add in 5% to it. So we want really 105% of the loan, right? So in our calculator, that's going to look like 1,000 times 1.05 because we can't type it in with the percent. We need to change it to the decimal. And so if we do 1,000 times 1.05, we will end up with $1,050 after 1 year. Then we would multiply this by 1.05 again, and we would get 1,102.5. Then we would multiply by that 1.05 again, and we would end up with 1,157.63. So what we're actually doing, right, is taking 1,000 times that 1.05 to the t power, however many times we needed to, because here you did it once, right, times 1.05, then you did it again, so that was timesing it by 1.05 twice, then again would be 3 times, so we would just do that t times. So similarly, for this next one, except for this time, we're doing it times 1.08 because we're doing it times 108%. So if we do this, we get 1,080 the first time after the first year. Then we get 1,166.40 after the second year. Then we get $1,259.71 after the third year. And if we do it for t years, right, we're multiplying by 1.08 t times. So then it says, which loan balance grew more quickly? So which one grew more quickly? How will this be visible in the graph of the two loan balances? So remember that this was B, graph B, and this was C. So in this case, C is growing more quickly. So C grows more quickly because it's at 8% versus 5%, right? And you can see it in the table that the numbers are bigger. And on the graph, this will mean C is higher than B or above B, which also means another way to say that would be that the y coordinate is higher. So at the same spot, the y coordinate of C is going to be above the y coordinate of B. Then it says using technology, create a graph that represents B and C over time. The graph should show the starting balance of each loan as well as the amount of loan after 15 years. So then it wants you to write down the graphing window needed to show these points. So I've graphed it here. We just need to go from 0 to 15. I like to see a little bit on the left side of the x-axis. So I just went from -1 to 16 for my x's. And then for the y's, I went from -100 to 3,200. Probably should have gone a little bit higher because when we look at 15 here, so when we look at 15, it's actually off the graph for C. So we don't actually see that. So I probably should have changed this to more like 3,500 or something to make sure that I can see that on the 15th year. You don't have to show below the 1,000. I just like to look at it. So I just like to start at 0 instead of zooming in. So it's up to you. You could have this be at like 800 or 900 so you can see 1,000 to wherever. Number 4, Lynn opened a savings account that pays 5.25% interest annually. And I'm just going to write this as a decimal. So remember, 1 divided by 4 is 0.25. So this is 5.25% interest. Then deposited $5,000. If she makes no deposits or withdrawals for 3 years, how much money will be in her account? So remember, the account is paying this interest. So they're going to give her back her 100% of what she puts in, right? So they're going to give her back all of her money plus an additional 5.25%. So that means that her account is growing by 105.25% each year. And then as a decimal, this would be 1.0525. So when we write the expression for how much she'll have, we have her original $5,000. Then that growth factor is 1.0525. And we want to know for 3 years. So then we'll put a 3 up here. That would be the expression to represent how much money she'll have. And then you would just type that into your calculator. And you would get that she has $5,829.57 in her account. Number 5, a person loans his friend $500. They agree on an annual interest rate of 5%. Write an expression for computing the amount owed on the loan after T years if no payments are made. So this means that, we're increasing by 5%. So the person is going to owe the 100% they borrowed plus an additional 5%. So each year they owe 105% of what they originally owed if no payments are made. And then 105% as a decimal is 1.05. So that's what we're going to want to type in or plug in for our equation. So we have the original loan at 500, and then that growth factor is 1.05, and then to the T. So this is how it's going to grow, provided that no payments are made on it. Number 6, select all of the situations that are accurately described by 15 times 3 to the 5th power. Part A says a population of bacteria begins at 15,000. The population triples each hour. How many bacteria are there after 5 hours? So this is just saying how many bacteria. So we'd be starting with 15,000. It's tripling for 5 hours. So this 15,000 does not match the 15, so part A is incorrect. Part B is basically the same. A population begins at 15,000. It triples each hour. They want to know after 5 hours, but this time it says how many thousand bacteria are there. So now we're not going to write out 15,000. We're just going to say 15,000 times 3 to the 5th. So we add the word thousand after. And so now we would just have 15 would represent 15,000. So this one is correct. C, a population of bacteria begin at 15,000. The population quintuples each hour. How many thousand bacteria are there after 3 hours? So again, 15 is good because that's 15,000. And then it quintuples. So our growth factor is 5 for 3 hours. So the growth factor and the exponent are switched around. So this one is not represented by that. D, a bank account balance is $15. The account balance triples each year. What is the bank account balance in dollars after 5 years? So our initial amount is 15. The growth factor is 3. It's tripling each year. And then for 5 years. So this one accurately describes it. A bank account balance is $15,000. It grows by $3,000 each year. What's the account balance in dollars, in thousands of dollars after 5 years? So this one we have thousands of dollars. So we want $15,000 and it's growing by $3,000 each year. So this means it's adding 3,000 in year 1, it's adding 3,000 in year 2, adding 3,000 in year 3, in year 4, in year 5. So this one is really 15 plus 3 times 5, not 3 to the 5th power. So E does not accurately represent it. Number 7, here are graphs of two exponential functions, f and g. If f of x is 100 times 2/3 to the x, and g of x is 100 times b to the x, what could the value of b be? So which of these would make sense? So now we know that f is above g, okay? So this means it's like these are decreasing, right? So it's falling or decreasing slower, okay? So it's decreasing slower for f. That means that g is falling or decreasing faster. And if it's decreasing faster, that means your b value is smaller. Okay, so like if we just talked about if this one's decreasing at half the rate, like if the decay factor is 1/2, then this one would be decreasing faster than that, meaning it would be a smaller number, like 1/10 of the size, okay, not a bigger number. So we want to look for a b value that's less than 2/3. And so 2/3, 1/3 is definitely lower than that. So that one would be good. And there's really only one answer. So this is the answer. 3/4, so 2/3 is 0.6 repeating. So if you wanted to look at 3/4 as a decimal, that's 0.75. That's bigger, so that's not good. 1 is definitely bigger than 2/3, and 3/2 is bigger than 1, so definitely bigger than 2/3. So A would be our answer. Number 8, the real estate tax in 2018 in a small rural country is increasing by 1/4%. So remember, 1/4% looks like this. And then as a decimal, if we divide this by 100, okay, meaning we move the decimal back 2 places, we end up with 0.0025 as the number version of 0.25%. Last year, the family paid $1,200 in taxes. which expression represents the real estate tax in dollars that the family will pay this year? So remember that they're going to pay their original 100% of what they paid the previous year, plus they're paying 0.25% more. Okay. And so if we think about this as decimals, this is 100.25%. So 100.25%. And as a decimal, that's 1.0025. Okay. So if we're looking at that, so let's select the ones that would make sense here. So this one is saying that they're doing 1,200 plus 1,200 times a quarter. Well, this is not the right decimal for a quarter percent. Okay, this is really increasing by 25%, and that's not what we're saying. So A, not good. B, not good. Again, that's 125%, not 100.25%. This one, not good. Okay, if we moved it over, this would be 102.5. And we want this one because this represents 100.25%. So 100.25%. Number 9, two inequalities are graphed on the same coordinate plane. Select all of the points that are solutions to the system. This means that they need to be in the overlapping region. So they need to be where they're solutions to both, which is going to be right here. So if we take a look at A, so A is the point 4, -6. Now this one is on the boundary. So this one is a solution to the solid line, but it's not a solution to the dotted line. So this one is not a solution. Okay, it has to be a solution to both graphs. This one is only a solution to the bottom one, not a solution to this top one. B is the 0.46. That's certainly not a solution. It's only a solution to the gray shaded region. C is the point -4.6. That's not a solution to either. Oh, sorry, -4, -6. My bad. -4, -6 is only a solution to this bottom one. So not a solution to the system. D is the point -4.6. That one, not a solution to either. So definitely not a solution to both. E is at 6, -8. That one's smack dab inside of that shaded region from both. So this is a solution. F is the 0.7, -9. So that's not easy to see. Okay, so that one's right there. And so that one's in the solution set. So that one's good. And then this last one, G, is at -8.6. And that's bad. Not in either set. So E and F here are the solutions.